I'm going to describe covalent bonding for you. My video probably is not going to be quite as much fun as the one that you watch for ionic bonding, but I couldn't find a really good covalent bonding one that didn't have a bunch of extra material in it. So with the ionic bonding, we diagrammed atoms, or you watched atoms being diagrammed, and you learned that they formed because sodium had one extra electron, and it would allow chlorine to have that one, which gave it 8. And when it gave away the electron, this became the outer energy level, which stabilized it. When chlorine attained the extra electron, it gave this shell 8, which stabilized it. But in that process of changing electrons, transferring electrons, the sodium atom lost a negative electron, which meant that it had one more positive charge than negative charges, so it became a +1 ion. Chlorine had 17 positive charges. When it gained the extra electron, it then had 18 negative charges, and it became a negative ion. And the opposite charged ions attracted, which pulled the two atoms together, forming an ionic bond. And this basically happens between metals and nonmetals. Now, this is transferring electrons, or someone will call it gaining, losing, transferring. That's how an ionic bond forms. The covalent bonds, co referring to sharing, valent referring to the valence electrons. So this is going to be sharing valence electrons, which, remember, the valence electrons are just the electrons in the outer shell. And this basically happens between nonmetals and other non-metals. Okay. So I mentioned the water molecule in the last 2 videos ago, and that's a covalent bond because the hydrogen and oxygen were both nonmetals and they were going to share electrons. So I'm going to start with a very basic covalent bond demonstration here. So you've heard of us talk of hydrogen gas, and when hydrogen gas is by itself, 2 atoms of hydrogen will bond to form an H2 molecule, which stabilizes the hydrogen. So when we talked about hydrogen gas, when we diagram hydrogen, hydrogen has the atomic number of 1, so it had 1 proton, and it had 0 neutrons, but it has 1 electron. And when hydrogen atoms are allowed to be around other hydrogen atoms, they each have 1 electron, but for them to be stable, they really need 2 electrons in this outer shell. If you have 2, they're both stable. So what will happen is that they will share an electron, and this electron is allowed to orbit that atom. This electron is allowed to orbit that nucleus. And when that happens, they both have access to 2 electrons. Their outer energy levels are filled and they're stable. You will often see them diagrammed or written like this: one dashed line equals 1 pair of electrons being shared, 1 pair. Now, let's talk about another set of molecules where you might have a double bond. And a double bonded molecule would be like oxygen. Oxygen has 8 protons. It will have 8 neutrons. Therefore, it has 8 electrons. 2 in the first energy level. And here's a writing a 6. I'm going to draw these out. 6. And we're just going to allow oxygen molecules to bond, or oxygen atoms to bond with other oxygen atoms. So they all have 2 in the first energy level, and this oxygen atom will also have 6 electrons in this outer energy level. Now they're going to be spaced out evenly all the way around the nuclei of the atoms, but to make it easier to show you how they're shared, I'm going to just load them up right here for right now. Okay, so they both have 6 electrons in their outer energy level. And if this one just gave this atom 2, this one would be stable and this one would not be stable. So, and because they're atoms of equal size, they both have the same number of positive charges, which are making an equal attraction for the electrons here. So what they will do is that they will share electrons. So if they just shared one pair, then this atom would have access to 2, and then would have 1, 2, 3, 4, 5, 6, 7. And that does not give either one of them a filled outer shell. But if they share another pair of electrons here, then these electrons can also orbit the other atoms, the other nuclei, and therefore it gives them access to 1, 2, 3, 4, 5, 6, 7, 8 electrons in their outer shell. That stabilizes them. And so you would represent oxygen with 2 dashed lines because 2 dashes equals 2 pair of electrons being shared, which is a total of 4 electrons. And you could go on and draw one with a triple bond also. That would be nitrogen. Nitrogen would share 3 electrons between 2 atoms, and that would stabilize it. So there are things called triple bonds also. Now, to talk about water, because water is really important to living things, just to show you how this works. Oxygen, once again, has 8 protons. We'll have 2 in the first energy level, and then it'll have 1, 2, 3, 4, 5, 6. So if oxygen's allowed to bond with hydrogen, and each hydrogen only has 1 electron out here, and it's not of any advantage for hydrogen to give its electron away because that's not going to make it stable. So what will happen here is if they share electrons between these atoms, if this hydrogen shares its electron with oxygen, that gives this hydrogen access to 2 electrons in its outer energy level, and it's stable. This gives oxygen access to 7, and it's not stable, but it can form another bond with this hydrogen. So this is hydrogen, and this is oxygen. So if it shares a pair of electrons here, that gives it access to the 8 electrons, the 6 here, 7, and 8. And so when you draw a structural formula, which is what those are up here, those are structural formulas. When you write H2, that's a chemical formula. This becomes O2 chemical formula. This here, the structural formula, because there's just one pair of electrons being shared. That's the structural formula for water, and that's the chemical formula for water. So basically, covalent bonds, they share valence electrons to fill the outer energy levels, and that stabilizes the atoms. So that's how covalent bonds work.